everyone. Today we will discuss the last chapter of this semester. So this is the material for chapter 6 of the textbook, and this will be the last topic we will see for 421. The remaining chapters will be discussed in 422. So the topic of chapter 6, which I think is one of the more complicated or one of the most complicated topic of this class, has to do with deriving the distribution for functions of random variables. So up to now, we have discussed, say in chapter 4.3, discrete or continuous random variable. In chapter 5, we discussed bivariate or multivariate random variables. But we have never talked about a general way to derive distribution for functions of these random variables. So the overview is as follows. Suppose we have a collection of random variables, x1 to xm, m of them. The main focus of this chapter, or chapter 6, is to describe techniques for deriving the distribution of x, where x is a function of these m random variables. So the methods in chapter 6, while they are applicable for general m and for any kind of random variables, in practice we will only consider the special case of continuous random variables, or either a function of a single random variable or function of two random variables. And the reason why we talk about continuous is it turns out that in many problems, integration is technically a bit easier than summation. That may be surprising to you, but it turns out that when you talk about functions of random variables, integration is a more general operation. So in the case when m equal to 2, we're even more restrictive. We usually restrict ourselves to either adding two random variable, subtracting two random variable, multiplying them, or dividing them. So like I said, the techniques are applicable in general, but most of our examples, in fact, most of the examples in statistics turns out to be quite more simpler. So either summation or even multiplication. So the methods are broadly grouped into maybe like 3 different techniques. First, the technique for deriving the cumulative distribution function, the probability that capital X is less than number x, and then taking the derivative to get the PDF. So this is section 6.3 of the textbook. The method of Jacobian, in the case when f is an invertible transformation, could be possibly bivariate. This, I think, is the technique in, 6.4. And the method of moment gating function, which I've seen before, this is a technique in 6.5. There's also 6.6, which we will discuss briefly, based on Jacobian for multivariate. And then later on, we will talk about order statistics, which is section 6.7. So let's start with the simplest operation possible. Convolutions, which has to do with a sum of two random variables. So the simplest transformation, that is adding or subtracting two random variables. So we first discuss the result in the case of discrete, and then we see that the similar result can be extended to the case of continuous. So I have x1 and x2. They are discrete random variables. And so suppose I have the marginal PMF, which is P1 and P2. And now I consider x, which is just x1 add to x2. Then I claim x has PMF, probability mass function, given by Px, the probability mass function for x, PMF for x, can be written as the sum over the x1 of the joint PMF. So here we see that x1 plus x minus x1 will equal to x, obviously. So this just says sum over all the value of x1. Now if you have x1, then x2 has to be such that x minus x1, which is x2, the sum has to be equal to x. So in the case when we do not assume that these random variables are independent, then by using the notion of conditional PMF, we can write this as of this form. So as we see, the joint PMF can be written as the marginal PMF, marginal, multiplied by the conditional PMF. And this is the topic of chapter 5. So the summation, we just have to be careful, is once again over all x1, for which the probability mass function is bigger than 0, just to avoid, again, summing over possible uncountable set. Like I said here, P2 given 1 is just a conditional PMF of x2 given x1 equal to the value little x1. In the very commonly used case, when x1 and x2 are independent, in which case the conditional PMF is the marginal, then this reduced down to the product of the marginal for x1 multiplied by the product of the marginal for x2, making sure that x1 plus x2 is equal to x. So this equation here is known as the convolution formula for independent discrete random variables. So in a sense, we have seen this operation before several times, so we will revisit those examples later in these slides. So the proof of this result is quite elementary. Because x1 and x2 are discrete, we could just count the possible combination. So if x, the sum is equal to little x, that means that I just have to sum over all possibility for the value of x1. So x1 equal to little x1, in which case x2 have to be the difference between x and x1. And then I could then move this out by using conditional probability, and then using this as P21, which is now the formula that I claimed earlier. And then once again, in the case of independence, I have what I said before. So let's see an example. So the first example is quite elementary. Suppose I have x1 be discrete random variables that is uniform, discrete uniform on 1, 2 up to m1. So that what that means is a probability that x1 is equal to any number I is equal to 1 over m1 for I from 1, 2 up to m1. So x1 is discrete uniform, and similarly x2 is discrete uniform for j from 1, 2 up to m2. And I assume that x1 and x2 are independent. First, assume for simplicity that the number of trials in m1 is less than m2. For example, I could think of that is like x1 is say maybe like roll a 4-side die affair, and maybe x2 is roll a 6-side die, and I want to look at x is the sum of faces. So in that case, x equal to x1 plus x2 has probability mass function given as follows. Once again, I sum over all the possible value of x1 of the marginal PMF for x1 multiplied by the marginal PMF for x2 averaged at x minus x1. So I could say, okay, so sum of x1, that's easy. I just have to sum x1 from 1 up to m1. That's all the possible value of range. And then I look at P2 of x minus x1. But now I have to be careful. The reason why I have to be careful is because I know that P2, J, is equal to 1 over m2 if j is in 1, 2 up to m2 and p2j is equal to 0 otherwise. So I have to be careful of the value of j. So that's why I could do 1 divided by m2, but I need to make sure that x minus x1, which is the value here, lies between 1 and m2. And so this is where we have to be a bit careful. So let's see an example. Let's go back to maybe say a more simpler example first. Suppose I let m1 be equal to 3 and say m2 equal to 4. So now let's say that x could now take on the value. So x equal to x1 plus x2. And then I could then let x here belongs to what the possible value. I could have 1 plus 1 is 2, 3, 4, 5, 6, and 7. So if I let x is equal to 2, I will have two values, that is x1 equal to 1, x2 equal to 1. X is equal to 3, I could then have the value x1 equal to 1, x2 equal to 2, or maybe let's write it as 2, 1. So either 1, 2 or 2, 1. X equal to 4, I could then have the value 1, 3, 2, 2, and 3, 1. And x is equal to 5. Now this is more interesting. I could now have 1, 4, 2, 3, and 3, 2. I cannot have 4, 1 because 4, 1 is impossible because x1 is less than or equal to 3. So I cannot have 3 possible combinations. And x equal to 6, I cannot start from 1 to 5, so I can only start from 2 to 4 and 3 to 3 because 1, 5 is not a possibility. And similarly, say 4, 2 is not a possibility. And finally, x equal to 7, I would then have roughly 3, 4. So if you look at this one, you see that the possible combination, so I say that x is equal to 2 has PMF 1 over 12, x equal to 3 has PMF 2 over 12, x equal to 4 is 3 over 12, x equal to 5 is 3 over 12, x equal to 6 is 2 over 12, and x equal to 7 is 1 over 12. So if we use this shape, it will now look like a trapezoidal. So this is the PMF. X is 2, 3, 4, 5, 6, 7. And at x equal to 2, I have 1 over 12. Then I go to 2 over 12. Then I go to 3 over 12. Then I stay the same. And now I go back and I go back. So if I draw the line, of course, there's no PDF, but I could draw a line. The line will look something like the shape of a trapezoidal. So 0 here is jumped to here. And this is the shape of a trapezoid. In the case when M1 equal to M2, the shape will look like triangular. In the case when M1 equal to M2. Otherwise, you will get a trapezoidal shape. And that is exactly what happens here. In the case when x lies between 2 and M1, you will have something that is increasing, x minus 1. So you have increasing. Between M1 plus 1 to M2, it will be 1 over M2. So you have horizontal. And then after that, M2 plus 1 up to M1 plus M2, you get M plus M minus X plus 1. So you'll be going down to 0 again, to 1 again. And that exhibits the pattern of a trapezoidal. So that is in the special case when M1 less than or equal to M2. In the general case, where possibly M2 is bigger than M1, then we just have to do a simple replacement. So if M1 is less than M2, you will use M1 So therefore, you can replace M1 with the minimum of M1 and M2. And then you can replace M2 with the maximum of M1 and M2. In which case, the general form looks like this. So this is known in the literature as the, let me just check sure that I go look at the right document. So this is known in the literature as the trapezoidal distribution. In the case when M1 equal to M2, it is known as the triangle distribution. So the sum of two discrete uniform follows the trapezoidal distribution. So note that this is not hard, but it's just very, I wouldn't say very, but you need to be a bit careful. So if you write down the special case first and then reason it through, you can easily extend it to the general case. But one need to be a bit careful. So a simpler example perhaps is suppose x1 is binomial, NP, n trials, success property P. x2 is m trials but with the same success probability P. And you have x1 is independent of x2. Then earlier we already know that x, which is x1 plus x2, is binomial. N plus m over P. N plus m trials and success probability P. So let's verify that. So we say, once again, the property that x equal to x, little x, I can sum over all the value of x1, of the marginal for x1, and the marginal for x2, evaluate at little x minus little x1. So the marginal for x1 is simply this. The marginal for x2, taking on the value little x minus x1, is once again here. And so I could combine p little x1 with p to the x minus x1 to become p to the power of x. And I can do 1 minus p n minus x1, 1 minus c m minus x minus x1 to become 1 minus p n plus m minus x. And then I can move both of those outside the summation because they do not depend on little x1. And I have the summation inside here, which depends on x1. And now I could then invoke Van der Monde identity in chapter 3 to show that this sum is nothing more than n plus m choosing x. And so I have this is nothing more than the PMF of my binomial n plus m trials and success probability P. So the nice thing about here, and the thing that is very interesting about here, is by the definition that I know, is that n choose r is 0 if r is less than 0, or if r is bigger than n. I don't have to worry about the limits of summation. Earlier, when I was doing the discrete uniform, I have to worry about this limit of summation, and that creates a bit of a mess. I have to try to keep track of it. But here, in the binomial, by using this convention, I can implicitly don't have to worry about the limit of summation, and things turns out to be easy. So let's do another example. So I see that x1 plus x2 is binomial. So you may say, what about x1 minus x2? Summation is binomial, so difference should be simple also. And that turns out to be sadly not the case. So x1 is binomial, x2 is binomial, and I look at the difference between x1 minus x2. Well, I could write this as x equal to x1 plus y2, where y2 is just simply minus x2. So then y2 has PMF of the form say f of y2 is equal to f of x2 of minus y2. For y2 takes on the value less than or equal to 0, and so minus y2 takes on the value bigger than or equal to 0. So once again, in that case, instead of using x minus x1, I have to replace it with x1 minus x. See, before you have x minus x1, now we have to replace it with x1 minus x. So I sum over x1 again, the marginal PMF for x1, the marginal PMF for x1 minus x. But after I do some simplification, I get this sum. And this sum, now the inner sum here, is no longer simple. I can no longer invoke the van der Waals identity. So I cannot simplify further. I get something that I can write down, but it doesn't look anything like anything I know before. It doesn't look binomial, it doesn't look, say, Poisson, it doesn't look negative binomial. It is just whatever it is. So in a sense, the distribution of x1 minus x2 has no simple name or no simple form. So as we can see, the summation may be simple, but the difference might not be. And you should be able to come up with examples of which the difference is simple, but the summation is not. Okay, so now let's just move on to talk about the convolution for continuous random variables. So you might also want to take a look at problem 6.66 in your textbook. But in any case, suppose I have a bivariate continuous random variable, and this bivariate random variable has a joint PDF little f x1 x2. Then the sum of the random variable x1 plus x2 will now has a PDF that looks very much like just replace the sum with an integral. So here I integrate with respect to the marginal for x1 and the conditional for x2 given x1. So where here x2 here is supposed to be x minus x1. So here what I mean here is this one is x2 is x minus x1. Is a conditional PDF of x2 equal to x2 minus x1 given x1 equal to x1. So in the case when the x1 and x2 are independent random variable, in which case the conditional PDF f2 given 1 is the same as the marginal PDF f2. I will have this expression here, which looks exactly like the convolution for discrete random variable. Well, once again, I replace summation with integration. And so the proof is once again very simple. So I just need to guarantee the probability that x, capital X, less than or equal to x. So now I just have to worry about the limit of integration. So x1 can go from negative infinity to infinity, where I assume that the joint PDF is 0 if x1 and x2 is not in the support. So don't have to worry about the limit of integration. So x1 goes from negative infinity to infinity. But because x2 plus x1 has to be less than x, so x2 can only go from negative infinity to at most x minus x1. And then, assuming that these are independent, so we'll prove this only for independence. The normal case is the same. Assuming that these are independent, I can write this as f1 x1 times f2 x2. And because x2 goes from negative infinity to x minus x1, that is the same as the cumulative PDF, cumulative CDF, evaluated at x minus x1, because the inner integration goes from minus infinity to x minus x1. So that becomes the marginal CDF. And so to get the PDF, we just have to differentiate the CDF for capital X with respect to the random variable, with respect to the variable little x. So take the integration, the derivative of this expression here. And now I can move the integral I can swap the order of integration and differentiation with one another. Swap order. So now I can differentiate this. This is just a constant. I can move it out. And so if I differentiate d over dx of this CDF, marginal CDF, I will get the marginal PDF. And that is exactly the formula I set out to prove. So as you can see, the proof is very similar to the discrete case, just replace summation by integration and take the derivative accordingly. So let's see a quick example. We know that if x1 is normal, mu1 sigma 1 squared, and x2 is normal, mu2 sigma 2 squared, then we showed earlier that x1 plus x2 is normal. And we show that via moment generating function. Shall I show the same thing, but now via the convolution formula? Reprove this via convolution. So the idea is once again very simple. We write fx as integration from minus infinity to infinity, f1 x1, f2 x minus x1, dx1. So this is f1 x1, and this is f2 x minus x1, and you integrate it with respect to dx1. So the next thing that you have to be careful, so let's erase this, we don't have to see that now. So you can move these two constants outside, and now you integrate this by saying that exponential, the product of two exponential is a sum. Well, that's a sum. Integrate this with respect to dx1. But the key point here is that this integration looks scary. And I wouldn't say that scary, but quite tedious. So it takes quite a bit of time to simplify it. But if you know, and if someone tells you how it is simplified, you could say, you could replace this inner squares by completing the sum of squares. It will look like this term multiplied by the exponential in the sum. So try to check that. So check this as a coffee break. So this is nothing more than a complete thing the square. So it's a little bit messy or tedious, but if I told you that the form looks like this, then you should be able to quickly check that it really is this form. So it turns out that the inner integration here can be converted into a change variable by defining u1 this way, where we define square root a is, as we claimed earlier, to be, where we defined earlier is a is sigma 1 squared plus sigma 2 squared divided by sigma 1 squared, sigma 2 squared. That's what we have here. So using that change of variable, in which case now x is assumed a constant, in this case. So the change of variable would say that the derivative with respect to x1 is the same as with respect to u1, and now 1 over square root of a. So you simplify this one out. And this turns out to be nothing more than an integration with respect to u1 squared divided by 2. And so, as we know earlier, that integration of e minus u1 squared divided by 2 du1 is nothing more than square root 2 pi. So we have here square root 2 pi compared to 2 pi here. And some simplification show that this is nothing more than the PDF for a normal with the variance being the sum of the variance. And so the general case just follows directly from adding everything by the mean. So this example here, conceptually, is not too difficult, but it is quite tedious. And the tedious part, the part that is tedious, is simply showing that this quantity here can be expanded out into this quantity and this quantity here by completing the square. So if you know that, or if you have seen that trick before, that will come to you naturally. And if not, well, this is as good a point as any to know this trick, because you will be using many of these kind of similar tricks in, say, 422. Many times when you work with the normal distribution, really everything boils down to, can I complete the square? So I cannot emphasize that enough. Normal distribution is usually leads to some kind of complete the squares. Complete the squares. It's tedious, but it is quite straightforward. So as you can see, the proof here via convolution is maybe more messy than the proof via moment-generating function. But the moment-generating function is more, say, magic. You have to believe the two random variables with the same moment-generating function has the same distribution. And we never prove that. And we will never prove it in this class or even in 422, because it is quite a bit more complicated than our level of discussion. So let's do another example. Suppose now I have x1 and x2 be gamma distribution with the same, possibly different shape, but the same scale. So possibly different shape, but the same scale. So we want to look at the distribution for x1 plus x2. We know for moment-generating function, that x is also going to be gamma. So let's verify that. So once again, now we have to be careful. So we want to integrate from negative infinity to infinity. But really, because the support of x1 is bigger than 0, we really have to integrate from 0 to infinity. But because x1 and x2 are both positive, so x1 plus x2 equal to x implies that x1 has to be less than or equal to x. So our limit of integration really should be going from 0 to x. So that's why you integrate from 0 to x. So many of these kind of problems in convolution, you have to be careful about the limits of either summation or integration. So in any case, integrate from 0 to x. This is the marginal PDF for x1. And this is the marginal PDF for x2, evaluated at x minus x1. And so we could move out quantities that doesn't depend on little x1, such as alpha 1, gamma alpha 1, and gamma alpha 2, and the constant beta alpha 1, beta alpha 2 outside, and the exponential, this is exponential minus x divided by beta, minus x divided by beta. So now you have e to minus x1, and you have here minus of minus x1, so those cancel out. So therefore you no longer have e anywhere to x1, so you have this integration here from 0 to x. This looks like a beta integral, and it is if you do a quick change of variable. So with that said, let us erase this. So this integral here, we just need to say we can allow x1 be x times t1. So t1 is 0 to 1. In which case x minus x1 is nothing more than x 1 minus t1. So therefore we have x to the alpha plus 1, alpha 1 minus 1, alpha 2 minus 1. But the key point is that d of, say, x1 is x times d of t1. So you have an additional x here. That's why you have x alpha 1 plus alpha 2 minus 1. And then t1 and 1 minus t1, integrate from 0 to 1. But this is nothing more than the beta integral. So this is simply beta alpha 1, alpha 2, as we saw before. And some simplification yield you this, which is nothing more than, once again, the PDF of a gamma random variable. So once again, just to recap, the gamma integral that you, I guess, love in chapter 4 show up many times in statistics. So it pays dividend to really remember the gamma integral and correspondingly the beta integral. But maybe after you take 421 and 422, maybe you can forget all about the gamma and the beta integral. That's fair. But at least for 422, a good way to maybe be well prepared to do some of the derivation in 422 is to remember your beta and gamma integrals. So you may want to now take a coffee break and look at example 6.3 and derive the PDF for the sum of two uniform random variables that are independent. And in a sense, I hope that was a fun coffee break. In fact, I lied a bit. The problem turns out to be a bit harder than it appears. And the reason why it's harder is, once again, is that the limit of integration, you have to be careful. Be careful of the limit of integration. So the answer is, once again, a trapezoidal distribution. So the PDF looks like this. So this is fx. Looks like this. And it starts at, say, 0. It increasing up to a. It goes from a to b. And this becomes a plus b. Of course, figure not up to scale. But the idea is that the PDF looks like a trapezoidal distribution. And you can derive that it is given by this. So once again, that's why I said, be careful with the limit of integration. You should consider three cases for when x is less than minimum AB, for when x is between the minimum and the maximum, and for when x is bigger than the maximum, up to the maximum possible value, a plus b. So if you have split it out into those several cases, you will see that it is obviously clear that will be trapezoidal distribution. But once again, like I said, if you have seen this problem before, you're going to know how to do it. If you don't, if you have not seen it before, well, it will be a little bit, say, tedious. Okay, so we have talked about the sum. So let's talk about the difference. I have x1 exponential with rate parameter lambda, and x2 is also exponential with the rate parameter lambda. So I know that x1 plus x2 is gamma 2 lambda, because an exponential, or 2 1 over lambda, because I know that exponential lambda is gamma 1 1 over lambda. Shape alpha, scale 1 over lambda. So what is the distribution of x1 minus x2? Well, I know that I can define x1 minus x2 as simply x1 plus y, where y is minus x2. So the PDF of y, which is minus x2, is simply the PDF of x2, but now where I assume that y has been less than 0, because I remember f2 of x2 is lambda e minus lambda x2. So now I need to minus the squared swap to be no minus here, and the support is from y less than or equal to 0. So the PDF, I can now write it simply as integration of from negative infinity to infinity of f1 x1 and f of y of x1 minus x dx1. But because x1 is exponential, so the limit of integration has to be replaced from 0 to infinity. That's what happens here. But now I have to be careful about the values. So x1 minus x2 can take on any value in from minus infinity to infinity. Because I could let x1 be 0 and x2 converges to infinity, or I could let x2 be 0 and x1 converges to infinity. So I have the range x1, x2. The difference could be anywhere between negative infinity to infinity. So if we have to consider the first two cases. The first case is x bigger than 0. Then this PDF for y, which is x minus x1, is non-zero if and only if x minus x1 is less than or equal to 0. That's what I said here, which requires x1 to be bigger than x. So if x is bigger than 0, I have to integrate from limit of integration from x to infinity of this product of the marginal PDF for x1 and the marginal PDF for y. And this integration is quite simple. You can check. The answer is lambda over 2 e minus lambda x. So note that the hard part of this problem is not the integration. The integration is easy. It's the limit of integration that is hard. So the limit of integration is the hard part. And you can check this, look also in your book, also in textbook. But for many of these problems, the hard part is to determine the limit of integration. So you have to be careful. So the book gives you a few figures or examples to show things. But in general, really, it all boils down to experience or being careful about things. Okay, so the next case is suppose x less than or equal to 0. Well, if x less than or equal to 0, because x1 is bigger than or equal to 0, in which case x minus x1 is always less than or equal to 0. So this is true for all value of x1 bigger than 0. So in that case, I could replace the limit of integration from 0 to infinity in the case when x is less than 0. And this integration turns out to be equally simple. But now I have this here, e lambda x. Let's check. Earlier, I have e minus lambda x. So in summary, I have x bigger than 0. It is lambda over 2 e minus lambda x. If x less than 0, it is this term. So in summary, no matter what the value of x, I could just replace x by its absolute value and put a negative in front. So the collecting the two cases, I get this is the PDF. And if you check this with a problem in chapter 4 of your textbook, this is known as the Laplace distribution. The mean is 0 and the scale is 1 over lambda. So the difference of two exponential has a Laplace distribution, and furthermore, it is symmetric. So fx is equal to f minus x. So the difference is symmetric around 0. And this trick is done quite often. If you have one random variable and you have another independent copy of it, the difference is always symmetric. Okay, and then you can have another example where you could do a random variable x, which is the sum of two random variables, one of which is discrete and another one that is continuous. So x1 is Poisson, which is discrete, x2 is continuous, then the sum is also continuous. And now instead of the normal convolution formula, you will have a slightly different convolution formula. So this is the convolution formula for the sum of discrete and continuous. You can check. And so if you take the derivative, you get this weird, I wouldn't say weird, but you get this mixture of PDF. And you can check the derivation. But in any case, just to illustrate that this looks weird, suppose I do a sum of a Poisson with rate parameter 4 and a sum of a normal with mean 0 and variance, I think 0.09. Then the PDF of x equal to x1 plus x2, where x1 is Poisson, x2 is the normal. This is how it looks like. It is a weird shape oscillating around. So in any case, the main thing I want to emphasize is that adding two simple random variables could give you something much more complicated. So that is why in many statistic problems, you can generate a very, say, sophisticated distribution by just doing some simple operations to simple distribution, like how the binomial is a sum of binary, or how the negative binomial could be generated from a Poisson with a gamma. And there are many other kinds of examples.